Let's look at another example of being able to solve a differential equation analytically. In this example, we have x double dot plus 5x dot plus 6x equals 0. So our independent variable is time, or t, and our dependent variable is x, and we have not only its first derivative, but its second derivative as well. We have two initial conditions. We have x of 0 is 1, and x dot of 0 is negative 1. And we want to solve for what is x of t. Again, in your differential equations class, if we have this second order differential equation, we have kind of a standard way that we're able to solve it, which we'll go through quickly. If you haven't had the class yet, don't worry, because we're going to be doing everything numerically for this course. All right, so we can take our equation and we can find that characteristic equation. So we can express this as lambda squared plus 5 lambda plus 6. So we have a lambda for each derivative we have of x. So we have a double derivative, so that's a lambda squared, plus 5 times first derivative is a lambda, plus 6 equals 0. And we can solve this for lambda. This is factorable into lambda plus 3, lambda plus 2 equals 0. And we can solve for the lambdas that make this true, or the roots, negative 3, negative 2. And we know that for a second order differential equation, if we can find those roots, then the standard form of our solution is going to look like some constant a times e to the negative 3t, that negative 3 coming from the first solution, negative 3, plus another constant we don't know yet, b, times e to the negative 2t. Again, that negative 2 from the second solution of lambda. And we can have more complicated ones where we have sines and cosines. We won't get into those here. We will get into those when we get numeric solutions. But this is our general solution for what x is. It's in the form of a e to the negative 3t plus b e to the negative 2t. And we still need to determine what the constants a and b are. And for that, we use our two initial conditions. So we know that this x has to satisfy both conditions simultaneously. So if we look at the first initial condition, this x evaluated at t is 0 has to be equal to 1. So if I plug in 0 for t into my equation here, I'm left with a times e to the 0, which is 1, plus b times e to the 0, also 1, or simply a plus b. So a plus b must be equal to 1. I have a second equation here that x dot of 0 is equal to negative 1. So if I take that x of t expression in the lower left and I differentiate once with respect to time, and then I evaluate that at t equals 0, I'm going to get negative 1 is equal to, that negative 3 comes out in front, so negative 3a times 1, minus 2 times b times 1. Again, that negative 2 comes out in front when I differentiate x of t. So if I simplify all this, I get negative 1 is equal to negative 3a minus 2b. So if I look at these two equations, one is a plus b, and negative 1 is negative 3a minus 2b. I have two equations for these two unknowns, a and b, which I can solve simultaneously. And if I do so, skipping a step here, I get that the value of a that satisfy these is 1. I get the value of b that satisfies both of these is negative 2. So I can solve for a is 1, b is negative 2, and that is going to mean that I can rewrite x of t as e to the negative 3t minus 2 e to the negative 2t as the solution to this differential equation. Again, what we would want to check is that it satisfies the initial conditions, and it does by design. If we evaluate this at 0, we get negative 1, and if we evaluate its derivative at 0, we get negative 1. Sorry, if we evaluate it at 0, we get a positive 1. And also, if we take this expression and put it back into that original differential equation, so we take its second derivative plus 5 times its first derivative plus 6 times its value, we're going to see that it's going to be equal to 1. And then we have our solution for x of t for this problem.